Hello everyone, this is Olivia. In this lecture, I will go over similarity and K nearest neighbor, and these are concepts that you will apply in assignment 6. The topics today is first to talk about the potential uses of similarity, and you'll find there is a wide range, and that is why for a lot of data scientists, similarities is one of our favorite metrics or topic. And so we'll talk about how to measure similarity using distance functions with some examples. The focus will be on how to use similarity to make predictions amongst different tasks, but mainly in this class, in this lecture, we only focus on use of K-nearest neighbor, which is also called KNN for supervised learning. So we'll talk about nearest neighbors, the use of them for predictions, and how, and as part of the predictions, how to estimate target values using examples. What is unique about KNN and some of the parameter selections, such as how many nearest neighbors, that is what K stands for, and some other factors. Lastly, just comment on a couple of commonly known issues with KNN that we should watch out for. And lastly, I will just talk about the KNN function that you will use in R for your assignment, which is different from what is used in chapter 3 of the book. And Yuan Yuan has already recorded tutorial on sample code for KNN based on using R Weka, and I want to explain a little bit why we are using that this semester. The main reference for this lecture, the best one is concepts mainly are well covered in chapter 6 of Data Science for Business, even though very similarly chapter 3 also covers these concepts, but I think if you only go to chapter 6, that will be sufficient. The sample code in chapter 3 is also posted in our Canvas for your reference. We will not use it, and we will not go over the sample code from chapter 3. The sample code posted based on chapter 3 has also been enhanced for more prediction performance evaluation. Okay, so there are a number of tasks that oftentimes businesses may be interested in, or different kind of applications. One is just finding things that are similar, and that will become foundation for other tasks. But this task itself can also answer some business questions, such as which companies or which business customers are similar to IBM's current best business customers, or which pages are most similar to this particular web page that I am looking at, so I want to find some others. Which books are most similar to the current book based on digital content. So there's so many applications are built on answers to these questions. Some examples are the following task. For example, once you can find what is similar, then we can make classification or numeric prediction estimation based on the classes or the target variable values of similar objects or similar customers. Those similar objects or customers are essentially the K nearest neighbors. The next task is also one that we will look at, not today, but next time, based on similarity, is that knowing which items are similar will group similar ones into single clusters and dissimilar ones into separate clusters. That's a task called clustering. And what probably has made Similarity and K-nearest neighbors most famous is the popularity of recommenders that tend to recommend movies or products that are similar to what a customer already likes, or or products that other customers similar to this one may like, or products other similar customers like. These are widely used by a lot of e-commerce websites, Netflix and Amazon, but also for other products or application domains, including dating in websites, including matching jobs with applicants. So this has a lot of monetization potential. The last is one that has been around for a long time, and it is a methodology also based on similarity, which we will not get into, called case-based reasoning. Cases are focused on similar cases, and this really has been used and being appropriate for a number of domains, but in healthcare or in legal area, the trainings of doctors and lawyers have already emphasized on finding past legal cases, for example, that are similar to one that's being learned, or a new one that needs to be handled. Same thing with doctors' training. In medical training or residency, there's a lot of focus on finding and looking at past patient cases, and to learn from those cases, that's how we can handle new patient cases. So then, since similarity is important, the first thing we learn is how to measure similarity. And this actually is, in my opinion, pretty straightforward using distance function. In other words, is that when we want to compare two objects, and in any data mining task, the objects or records are described using a number of attributes or variables. For example, age, spending, gender, income, and etc. And when we want to compare the similarity between two objects or two customers, and then a quantitative approach is use the values of these attributes to calculate and treat distance functions, treat them like different dimensions, each of these attributes like a dimension in geometric multidimensional space, and use their values as the value on the each space in each space, and then come up with a distance measure of the distance between two objects. If the distance is large, then the two objects are less similar, and if the distance is short, then the similarity is high between similarity between the two objects is high. So distance function is something we have learned in algebra or geometry. And just to review, there are a lot of different functions can be used to measure distance. We will be focusing on, and a lot of the implementations out there either just assume one or two, or give you a number of them to choose. Distance functions have these properties or the conditions that it must satisfy. It has to be non-negative, so there's no negative distance, but it can be zero. And specifically, zero is always true for the distance between the same objects, which means the distance from an object to itself is always 0. There's no other distance unless objects are exactly identical can be 0. So distance symmetric, meaning distance from point A to B is the same as the distance from point B to A. And the distance also means the famous relationship where in a triangle that the direct distance between any 2 points is shorter than the indirect distance by going from A, for example, to another point C, then go from C to B. So that is a distance, indirect distance by passing through another object C that is not on the segment between A and B. And so most of the time, actually, distance functions will be calculated for us, but knowing what has been used out there can be helpful. And also using the common distance functions such as Manhattan distance function, Euclidean distance function, to understand some examples could be helpful. And these two are also the most common ones. For example, especially this Euclidean distance function has been the most popular one used. So Manhattan distance function is based on absolute distances. So if two objects x and y have different variables, and currently we'll focus on numerical variables. So since categorical variables, as we will see later on, are need some transformation before calculating distance and using this type of function. So the attributes x1, x2, up to xn of object x are all numerical. Then the attributes the same attribute of y is y1. Then second one y2 and yn are numerical attributes of y. So the distance are looking at absolute values of pairwise, the distance or the difference between a pair of x value and y value for the same attribute and for all n of them. So this is first order difference in absolute, so you can easily verify that this is non-negative and symmetric and 0. It will be 0 if x equals to y, and other relationship that the direct distance is always shorter than the indirect distance between x and y. So now plugging this back to data we usually mine in data mining task, Manhattan distance, and if we are interested in 2 customers, and out of this, using only 2 attributes, predictor attributes, and not to worry about which one is target. Currently, we don't look at any target variable at this point in this example. So Manhattan distance will measure the distance between Sue and Carl, but based on the absolute difference between their ages, 21 and 27. So that will be 6, and the difference between their spendings, 2,300 and 2,600. So the distance between 2 of them is 306. You can apply this to others and to see who has the largest distance and who has the short, which 2 customers have the largest distance, therefore most dissimilar, and who have the shortest distance, and therefore they are most similar. The other is Euclidean, which essentially is the square root of the attribute values of object x and object y. So square root over the sum of the square of pairwise distance or pairwise differences for the same attribute between values from x and value from y. So attribute x1 value and attribute y1 value is for the same attribute. For example, age. This is the same attribute, but from x, for example, spending, and this is y from another customer, and it's also spending, and take the square and sum those up and take another square root. And it can be different order, but typically we just have h equals to 2, take a square root. Okay, so similar example, Sue and Carl. So square of the difference in age in their age is 6 square, and the difference square of the difference in their spending is 300 square. Then you take a square root of this total value. It will become 300 dot probably 0.6 or so, just round up to 301. There's something you can easily observe using Euclidean distance here is that out of these two discrepancies amongst attributes of Sue and Carl, spending difference dominate the distance value. So 300 and 301 here. So this could be an issue that no matter what difference age two customers have in their ages, it really would never affect the Euclidean distance significantly unless there's no difference at all in their spendings. So let me quickly talk about that's how data scientists or some functions out there will need to transform other types of non-numeric variables. For example, we oftentimes have attributes that are categorical with 2 values, such as marries. For example, just if we only want to know marry or not, gender types, only 2 types, home, internet, yes or no, then these are all binary. There are also other categorical variables that have more than 2 levels, and these levels sometimes have ordinal relationships. So we also call this ordinal variables, and the levels could actually be numbers, 7, 8, 9, 10. They can be treated like numerical, but if you want to keep them integer, then this also is nominal ordinal variables. 50 states in the United States or other geographical locations, these have a lot more values, and sometimes there's also some sort of order or some sort of meaning. And so there can be lots of ways to do transformation. The ones that we're most familiar with, that we kind of learn from regression models without directly doing transformation, but we witness and observe in the regression model summary that categorical variables has been transformed into dummy variables to indicate whether a dummy variable is equal to a particular categorical value, such as gender, such as region, northeast, northwest or not, and so on, so forth. So, sorry. And so that's one. There is also a way to directly decide on, measure the distance as 0 and 1. 0 essentially means no distance, meaning the same, such as the same state, same gender, same marital status, same home internet. This type, then so this should all be zeros. But if no matter which 2 states, as long as they're different, is the distance is 1, and different gender, different status, different home locations or homes, state, home city, and so home type, and so on. This is also another way has been considered, and it could be useful if you need to customize your own distance function to consider this. Some can be just transformed to some numerical values which represent the ranks, such as high is 3, median is 2, low is 1. And like I said, that some method will automatically do these transformations. And for that reason, I have chosen KNN implementation that will do that for you. So you won't spend half of your code doing transformations. And so this is just an example of, by considering other categorical variables, income, state, and gender, and based on, for this Sue and Carl, if we look at their income at the same levels, different states, and different gender types, using the second method, we can measure their distances based on these three variables as 0, 1, and 1. So the Manhattan distance value now become, sorry, it should be 308, not 3108. And the Euclidean distance should be, the Euclidean distance should be 301. So I think the problem I ask here, ask you to identify, is whether it is okay for the spending distance differences between Sue and Carl to dominate their distance value based on either Manhattan or Euclidean. And that depends on your applications. Oftentimes it is not. So this brings up the need for numerical and transformed categorical value normalization, standardization. So once all the variable values become numeric, then their ranges are different. Then we can do normalization, which is normally considered min-max. This is called min-max type normalization, is to find, set the minimum and maximum distance for any attribute to be the same. For example, the minimum distance is 0, and the maximum distance for any attributes can only be as high as 100, and preferably all at 100. So for example, ages, assumed distance typically is up to 100, or we can just normalize it to 100. Spending, we will normalize the distance, the max, to 100 by taking the maximum difference and divide it by itself and multiply it by 100, like this. 100, and then the maximum distance between spendings, is 7,000 and 2,300. This is the maximum spending difference. We normalize it to 100 by doing this way. So 300 over, I think 4,700 multiplied by 100. That will give you the distance in spending normalized. And 0 is still 0. And originally the difference between Sue and Carl in their state of residence is 1, and now it becomes 100. Gender is also 100. The other way that is very, very commonly used, and you can see some example of this, both of this type of applications in Chapter 3 of Machine Learning with R, is called Z-score standardization using this formulation. And this is a good understanding and good appreciation for what it takes to do K nearest neighbor or measuring distance correctly, either for supervised learning or later on for clustering. However, for you to get to better understand the performance outcomes and the use of performance outcome of K nearest neighbors method, I chose a method that would do this automatically for you. So you don't have to do categorical variable transformation. You don't have to do normalization, standardization, and difference in spendings, like large value, won't become an issue in dominating the distance. There are lots of other distance functions, which I also won't get into as you continue to use similarity in various applications, such as recommenders, soon later on in clustering, and text mining, and so on and so forth. More and more distance functions may make more sense for others. So I won't talk about this in Jacquard distance and other cosine distance and other distance functions you can find from either data science from for business text, machine learning with R, or other references. So now we get to nearest neighbors for predictive modeling. So the process, I summarized the process of doing supervised learning using nearest neighbors in these steps, and they're actually pretty straightforward. First, just to reinforce that when we talk by nearest neighbors, or NN, we mean that these are the most similar instances in the data set. And later on, we will be more specific. We are actually talking about the most similar instances to a testing or a new instance, and the similar instances are identified from training. So here we go. So the focus is to make prediction for data in the testing set or a new instance that we may not know. Eventually, when we apply it, we have a new instance, we don't have the label, and we want to predict the label. And so for every instance in a testing set, the similarity of a testing instance to every instance in the training set will be calculated. And you will do that, and if you have multiple records in the testing set, and if you're given that, and you can essentially calculate similarity between one training data or one training instance and one testing instance, and for every possible pair. This can be done all together and stored, and so that's also one of the reasons there is some good amount of memory requirement as a result of the approach that it takes. Okay, we'll get to that in a bit. So now so this part is applying the distance function to calculate similarity, and then to start making prediction. Now we will focus on one testing instance or one new instance at a time. So now we want to predict the target variable. Either it is a categorical variable or a numerical variable in the case of regression, classification of regression. Okay, so given this testing instance, now we'll go back to the similarities that were previously generated. We search through the similarities that correspond to similarities between this testing instance and the training instances. The purpose is to find nearest neighbors. Now, using K, meaning KNN works when a K is specified. So assume K is the specified, like either 3 or 10 or 30 is being given, then we will find 3 or 10 or 30 nearest neighbors in the training set. Once those K nearest neighbors are found, then the rest of the task is as simple as estimating the target variable value of this testing instance based on the K nearest neighbors on known target values. These are supervised learning, so training data and testing data have labels provided, so their target variable values are given. The difference will be, there's some difference between how you estimate this target variable value based on whether you're estimating a categorical value or estimating a numerical value. Okay, so we'll use an example first, talk about how to estimate categorical value. So, so this is an example from Data Science for Business, Chapter 6 and Table 6.1. So this is the training data: John, Rachel, Ruth, Jefferson, Nora. And these are the attributes: age, income, in thousands, and how many credit cards, and whether someone will respond to something, either like another credit card promotion offer, or some other you know, CD, certified deposit type of banking offer. So now the focus is the new instance is David. You can assume this could be a new instance. So David's age is 37, income is 50, 2 cars already, and either assume that this because this is a new instance, we don't know David's response, or we can assume David is a testing instance, we're just hiding the response, and because we want to estimate it and then do evaluation. So the distance between David and each of the 5 training customers, or 5 customers in training set, will be calculated using Euclidean distance functions based on age, income, and cars attributes. So be sure that only use predictors and not target variables in the distance functions. This one has not done normalization at this point, and this is a good point to show that, and to make some point about this, you can see that there are some good wide age differences, such as Ruth and Jefferson are 2 older customers, and their incomes, their income levels, 200,000, 170,000 are also significantly higher than others. But the gaps, or the difference, is larger in income than in age. So as a result, you can see from distance functions that the distance also between David and these 5 customers is also dominated by income. So David's distance to Ruth and distance to Jefferson are above 100, and 2 other 3, partly because their age, but mostly because their similarity in income level, they're all around, they're all 15 or less than 16, between 15 and 16. So if we look at, if we assume k equals to 5, then all these 5 will be nearest neighbors. If we assume k equals to 3, then only John, Rachel, and Nora will be the k nearest neighbor. So let's look at the case of all 5. Like if there are other customers, but these are actually the 5 nearest, 5 customers with the shortest distance values, then to estimate David's response, we will look at 5 nearest neighbors' responses. The majority class of these 5 similar customers is no. So the most common way of estimating categorical target variable of a new instance this way is to take the majority class. So David's response will be estimated to be no. However, if we assume k equals to 3, then Ruth and Jefferson drop out of John, Rachel, and Nora are the only other 3 nearest neighbors. The majority class now switch to yes, 2 out of 3. So David's response should be estimated to yes. So you can see that the difference in choosing k could make a difference in the estimate for a response, the estimate for a target variable. Okay. So to go back to for other tasks, which we will also try, but we won't go through the detail how to estimate the numerical a numerical target variable in regression models. And it's very similar. Out of k nearest neighbor, instead of using majority class, we can use mean or median or some of the functions. These two are the most common ones. And similarly, for classification, you can also, if you're interested in the probability that David belong to a yes class or belong to a no class, and can basically calculate the portion of the k nearest neighbor that has the majority class, which is actually, if k equals to 5, then it's 0.6. That's an example. Okay. So it's very, one of the reasons I feel it is very valuable for the class to know KNN, besides that KNN, that similarity has been a foundation for many other tasks, and KNN is one of the most popular method that uses similarity. Is also, it has some different, very unique characteristics compared to other supervised learning algorithm we have learned, decision tree, naive Bayesian, other black box methods, as well as regression. So the difference really has been related to the answer to this question. Does the training data train a model in no, in this method or using this algorithm? So let's think about that. By walking through what happened during the training phase. When you have a training data set, and the use of the training data by this KNN method is to find the similar customers or similar instances to a testing instance or to a new instance. So before you actually have a testing instance or a testing data set, there's no similarity to be calculated. So during training phase, the algorithm basically will import the data and and in its own internal data structure and store the training data. So we call this internal data structure in memory. And this term is used to categorize this, oftentimes to categorize this KNN algorithm because the need to store training data in memory. And that's it. Then you go on to prediction phase. So as a result, the answer is here. We actually don't do anything other than import and store because there's nothing you can do, not even to calculate similarities or distance functions. So as a result, it is pretty fast, but memory intensive because it depends on how large your training data is. So most of the work is here, which we went through on slide 16 already, where you know that once you get into prediction phase for your testing, given a testing data set or for giving a whole data set and you want to do cross-validation, and then now it will start to calculate similarity, find k nearest neighbor, do voting to estimate the target variable for every testing instance. And we saw the process on slide 16. We went through it, talk about it in using an example in slide 17. So this is the main work, and it's a lot of work to go through the whole training data set, either that being 10,000 records, 20,000 records, or or a small amount, and for every testing data set. So the main work is here and could be time consuming here. And so as a result, this unique characteristic to summarize, it really doesn't build a model, but although we will still call this training phase, similar to others, but the training here has somewhat different meaning. Unless we also want to do something else during training, which we will talk about later on. So common categorization is, this is a instance-based. So the prediction happen for when an instance label or target variable value needs to be estimated. So it's an instance-based learning algorithm. And instant-based IB is an IBL instance-based learning is one of the popular KNN methods out there. So oftentimes this type of algorithm out there are called KNN. The actual names are called KNN, or sometimes IBL. And because training data is stored in memory, so it's also called memory-based learning algorithms. And also because during training, there's the algorithm, this supervised learning algorithm in a way is lazy. It's just not, when others are very busy building a model, like decision tree, like naive Bayesian, like support vector machine, or neural network. This one does not do anything. So it's called lazy learners too also. Very interesting name. So now I want to talk about K. So to talk about K is also related to which K will give you good performance, and related to performance, we also want to see whether the performance is general to different data sets that this model may be applied to, or this method can be applied to. So we'll talk about the geometric visualization of the training space, and also to see from that visualization that how KNN model can potentially be overfitted to training data. And this is especially the extreme case is definitely when K equals to 1, which means that you're predicting an instance target variable value only based on one nearest neighbor. And so this is a figure from Data Science for Business by Provost and Fawcett. And there are also a lot of other similar diagrams, for example, from machine learning with our chapter 3. This is an example of using colors or shades or gray, and also shapes of the points or of the instance, such as squares, stars, and triangles. So 3 shades of gray correspond white for rectangles, and dark gray for triangle instances, and stars, and middle gray, shade of gray is the other class. And so these are data for supervised learning for 3 classes. So when you do KNN, when K equals to 1, or we say 1 NNN, single nearest neighbor, and this is the training data, the way to use one nearest neighbor to estimate the target variable, to estimate this training instance class, it will actually be using itself to train it. So this is because we're visualizing the training space. And so you'll find every single one of them will get their own class labels as the estimated class. So it's a perfect classifier for this training data set. And the separations amongst different classes using K equals to 1 is all just around groups of them or single ones of them. So it's very jagged, and it can be nested, can be embedded. It's not like lines or planes in KVM, in SVM, or segmented space using using the values of attributes. And this is really a very extreme case. You can see from this there could be very all kinds of concerns related to overfitting. So it could potentially overfit a lot because it will always try to since identify only one nearest neighbor and will select itself as its own nearest neighbor. And in training data, it works very well. It could potentially also work well when you apply 1NN classifier that to testing data. So 1NN has worked, and sometimes 1NN may be selected, or k equals to 1 may be selected. As you increase k, for example, in another figure, using k equals to 3, then you can see that the boundaries amongst different classes, and it's not, so now the colors are what is being predicted, and the shapes are the actual class. So you can see in the prediction for square class, there is 1 or potentially 2 errors. And in this, using k equals to 30, and in this area, for the stars that these stars are correctly predicted to be stars, but there are some triangles, that are predicted to be stars. And similarly in this area, triangles are predicted to be triangles, but stars also get predicted to be triangles. So just from this, you can see the prediction errors are higher, but the potential for this to be general to other data sets, given these boundaries, are higher, because it's really not cut around, the boundaries are not cut around just the labels, so that in the future, once the points move a little bit, then immediately the error rates shut up or increases. So this is a good way to visualize that the differences in k, that as you increase, performance may not necessarily improve, but it could be more generalizable, or it can be more general. And so that's the point. The boundaries get smoother, and which is good for possible higher generality, but it doesn't guarantee improved performance. So as a result, then it's really important for data scientists to search for a good K. There are some common practices that you can apply to choose decide on K. Some machine learnings researchers have proposed some using k equals square root of the size of the data set, either testing or training or whole data set. And I've been using mostly suggesting some k related to the size of the training set. And the other one is chapter 3 in machine learning with R also have advocated, and most data scientists have advocated, you really should set k to different values and make a comparison, and based on how accurate predictions are, and whether without having too much of an overfitting issue, or that the a good performance can still be general to various testing sets. So this we definitely can try. The other one is if there's some implementation already done, or if you would like, systematically evaluate every possible k. You don't do this to the infinite, but give a reasonable maximum k, and then start to evaluate from k equals to 1, which means 1 nearest neighbor, to 2, to 3, and then up to the maximum value, and then select the best k. And some method has provided this option. So for example, the KNN implementation in our website called IB instance-based learning, but instead of L is K to stand for different K that you can choose, allow this option. And so I'll just briefly talk about this. When you assign, so when you choose the feature or set the parameter setting to automatically select K, then K that is usually given in a KNN function is recognized as the maximum value as opposed to a fixed value. So let's try a variable called KK that we can change from 1 equals to all the way up to this maximum K. For every KK, then essentially you want to evaluate the prediction performance of a training set, because a function like IBK that we use, and we can choose this x equals to true to be the setting to trigger automatic selection of K, so that K equals to 40. 40 is the assumed maximum value of KK. And similar to other parameters, we change for other algorithms. We change them using wildcat control, and in the function, for example, in function IBK. And when you specify this is only sort of the training phase, not really training a model, but this is the phase. When IBK function is called, it's not testing phase. So there's no testing data given there yet. So this K will be selected using training data. And how do you evaluate the performance of different K? Then this is done by assuming our training data is testing data, one instance at a time, and the whole training data set is still the training data set, but pull one instance out. So this is actually essentially similar to what's called leave one out. This is the same as what's called leave one out cross-validation, and which I will just briefly mention. This is an old slide from we use. It's also from Data Science for Business. Talk about 5-4 cross-validation. But without changing this diagram, I just want to talk about this is cross-validation. Leave one out validation or leave one out cross-validation. Essentially, it's an extreme case, the most extreme case of cross-validation, which is the case which happens when you cut each record in the whole data set into a fold. So if the whole data set has n records, like n equals to 20,000, and then the number of folds in this leave one out cross-validation is actually 20,000 fold cross-validation, where each fold only has one record. So you will use all the rest folds to train them, or to not train, but to in KNN to be used to predict this, and then which is only one instance. And we talk about, because all the training data in this case is actually the whole data set. So sometimes the neighbor, the instance itself will also be identified from this training as its nearest neighbor. So it's not exactly the same, but it's similar to, because the training data set is actually the whole data set. So to go back and complete this is, as you finish through for each iterations, when K equals, when you increases K start from 1 and then increase by 1 to 2 and so on, then you will leave one out for every instance and then evaluate the performance, and you can calculate like average accuracy or average MAE or predictive errors, and then to for each KK. And so, for example, if KK equals to 1, I should give you the highest accuracy or the best average MAE. You may set, using this automatic selection, you may say KK equals to 1, or you may find KK equals to 30 compared to all the other possible KK will give you the best classification accuracy, right? Or the best other predictive error, or like MAE or RMSE, and for prediction errors, then you will select that KK. So this is an option that you can consider, and it will be interesting to see when a model, whether KK equals to 1, or oftentimes gets selected by this automatic selection of K for the data set. And one thing that I want to remind you is that IBK, when you use this option to automatically select K, it's very time consuming. So for our regression data sets, they're smaller, so this will go fairly relatively fast. But for classification data sets like income, like churn, like churn minority, they're all over 10,000 or some 20,000 or over 30,000. So you can sample down, or you can for your own testing, but for assignment, give yourself some time. You may walk away and come back to it. Okay, the last factor that will be good for KNN data scientists to try is whether to treat every single one of the K nearest neighbors the same when you use their labels, when the method uses their target variable values to estimate the class label or the numerical target variable value for a testing instance. And the answer is, yeah, you can change it, because some people will say for example, using this case, whereas from previous example, the 5 training data to David, their distance is if my K equals to 5. And so I'm looking at all 5 as the nearest neighbors. But then the way the label got skewed by the estimation got skewed by these 2 nodes and tipped the scale to with 1 more node, then the estimated label of class is null for David. So David is the testing instance or the new instance. However, this can be adjusted, or to be more fair, if we say, hey, actually, even though K equals to 5, Jeff and Ruth are not as close as the 3. So let's adjust their weight based on their distance to David. Okay, so the weight of them to David are adjusted. You can see this higher distance and lower weight, and shorter distance, higher weight, very similar. And you can do different functions to derive this. And this, the most important thing is that they come up, also translate to an amount that will be used to calculate the estimated numerical value or the class. So, so for example, we use this to come up with the final class probability estimate for David is the probability for the yes class now based on this contribution now is 0.65. So these two value total together. But for no, even though there are 3 labels or 3 customers, but it only total up to about 0.35. So the higher class probability, very similar to naive Bayesian, will be will correspond to the target class that you estimate. So 0.5 for yes class, and yes now is the predicted class instead of no, even though your k is still 5. You haven't changed that. Okay. So this type of contributions can, some examples are 1 over distance or 1 minus distance. These are functions that you can find in KNN methods such as IBK that is used from our WCAG that is used in this class. So, so this type of method is called weighted voting or similarity moderated or distance moderated voting. So as I mentioned, the way it works is to give more similar neighbors more weight out of the same k. And the weights can be these 2. And I just want to point out that in your IBK function, so this should be a capital B. And is the same, is how you can trigger the use of this voted weighting or similarity adjusted weighting. F equals to true is the one when you trigger this type of weighted voting approach. And if you don't have either one of this, then you're not using any weighted voting. You're just using, for example, majority or mean or median. And so as you could already see in the example, even though the how many neighbors, nearest neighbor, k is still the same, but using this could possibly improve the accuracy or potentially also increase model's generality. Okay, so we're almost done. Just to point out a couple issues. Most people would say nearest neighbor is not a really intelligent method because it doesn't have a model. So the lack of intelligence is mainly that you don't have the knowledge that is embedded in the model where you can see how tree is split, you can see the conditional probabilities and so on and so forth. But this is not too different in a way from other black box methods like SVM or neural network that you cannot quite explain the results or you don't have a model. And the fact that now more and more people find that making recommendations, for example, based on what other similar customers like, could be actually very useful. So that hasn't stopped KNN from being adopted. The other one is time complexity and dimensionality issue. Because distance functions are all based on attribute calculations, not like decision tree, it may deprioritize or prune out some attributes that don't have predictive power. But this approach, even if you have an attribute that's very noisy there, it will still be used. So be very careful with what you select, and also you could possibly think about using domain knowledge to do feature selection and also adjust your similarity and distance function. And lastly, as we already mentioned, that this can be computationally very time consuming. So besides when you try to automatically find the optimal k, but also when you do cross-validation and so on and so forth. So in your assignment 6, you will be asked to do 3-4 cross-validation for data sets size, data sets as big as 20,000 records. So again, give yourself some time, let it run. So don't wait until the last minute to test it, need the file before you submit the results. So this I have already talked about, that in based on my experience last semester, I feel that I do not, in this semester, I do not want the class to spend time right now writing code to normalize attributes, and also to learn the difference between using the functions in chapter 3 called KNN from the class package, which is different. And also KNN there has not been fully tested for numerical value prediction. We kind of try to find other, and we found something that worked, and but it's also a lot of explanation for the class. So as a result, starting from this semester, I'm not using this to save some time. Moreover, in the future, I would encourage you to learn more about normalization. If there, for some clustering packet function, for example, the one that is used in this k-means in this book, it also requires normalization, but there are others that don't. So, but learning more about normalization and z-score standardization is always good for data scientists, given our short time, our time pressure. So we will not. Instead, I use RWCA. As a result, you don't have to normalize, and you find that even though it is a lazy learner, you still have somewhat of a similar function structures or code structure using IBK, and then do evaluate WCAG classifier. In fact, in assignment 6, I extensively asked you to use evaluate WCAG classifier to shorten the amount of code that is required to get cross-validation results, and so on and so forth. It's really, in my opinion, easier to use. It can be used for classification and regression. It also have automatic case selection, and also allows for weighted voting. So those you will try in this assignment 6, and I hope you enjoy it more. And assignment 6 is actually has very similar data. I mean, use exactly same data sets as assignment 5, and the focus, except that the focus is on IBK, not on multi-layer perceptron, or not on KSVM. And you learn how to apply them and think about the issues with KNN, and try some of this parameter adjusting. Okay, that's all. Thank you.